Hi, today we're going to be talking about radioactivity. Now, last time we learned about the reasons why a particular nucleus will be nuclearly unstable. All right. Well, radioactivity is the response to that instability. It is a process during which unstable nuclei undergo spontaneous nuclear decay and emit particles and energy. Now remember, the instability is due either to improper neutron to proton ratio or to the fact that the nucleus is too large. Now remember, we learned that the instability is primarily when the ratio is different than 1.1. When you take the number of neutrons and divide by the number of protons, ideally you want it to be 1.1. Well, if this number gets either too large or too small, then it doesn't work. All right? Then it doesn't work. Then it becomes unstable. Also, the fact that the largest stable nucleus has a mass of 209, anything larger than 209 is going to indicate an unstable nucleus because it is too large. Now, the processes for fixing these problems, first of all, the overly large nuclei can be reduced in size by alpha particle production. And we'll learn more about that in a minute. Neutrons can be converted into protons using beta particle production. And this will make, since if neutrons are turned into protons, this will decrease this ratio and thus make it more stable. If the problem is you have too many protons, well, then protons can be converted into neutrons by either positron production or electron capture. Both of these also emit high energy gamma rays as a byproduct. So we're going to look at these in detail now. All right. Now, in the process of looking at these, to really understand what's going on in these nuclear reactions, I need to teach you guys how to balance nuclear equations. Now, balancing nuclear equations is very, very simple. All right. They are used to represent nuclear reactions. And you always start off by using the atomic nucleus symbols. So if you remember, an atomic nucleus symbol is when you have, let's say we want to do carbon-14. Well, carbon-14, which could be represented like this with the symbol and then the mass number. It could be called carbon-14 like that. But to do it as a symbol, you would have the chemical symbol here. In the top left-hand corner, we would have the mass number, okay? So in this case, it would be 14. So again, this would be the mass number. And then on the bottom, you would have the atomic number. And according to the periodic table, the atomic number for carbon is 6. All right. Atomic number for carbon is 6. And so that would go in the bottom left-hand corner. Now, oftentimes, this can be considered the charge as well. Since there are 6 protons, it has a positive 6 charge. And when you are balancing a nuclear equation, the trick to remember is on both sides of the arrow. So you have like your reactants and your products. Both sides of the arrow need to have equal masses and equal atomic numbers. That's the key thing to remember. So the sum of the reactants' mass numbers must equal the sum of the products' mass numbers, and the sum of the reactants' charges / atomic numbers must equal the sum of the products charges and atomic numbers. Now, to really understand how this works, I'm going to have to show you some examples as we go through. So we're going to start off with alpha particle production. Alpha particle production. Now remember, alpha particle production is the type of radioactivity where you produce, all right, this is what happens when you have a heavy radioactive nuclide, something over 209. And it results in the loss of 4 in mass number and the loss of 2 in atomic number. It produces what is known as an alpha particle. Now, an alpha particle is a helium nucleus produced in radioactive decay. Now, helium nucleus, symbol for helium is He. The mass, all right, since it has 2 protons and 2 neutrons, we add those up and we have a mass number of 4. And since there's 2 protons, an atomic number of 2. This, if you're just talking about radioactivity, this would be an alpha particle. All right. So this is an alpha. And just so you guys know, the symbol for alpha sometimes looks like that. It's kind of like a fat little fishy symbol or whatever. Greek letter A is an alpha symbol. All right. So basically, it's a helium atom nucleus. And when this occurs, when alpha particle production or alpha decay or alpha radiation, all of them are the same, it reduces the atomic number by 2 and the mass number by 4. All right. So an example, let's say we have radium 222. So the problem says, you might have a problem that says radium 222 undergoes alpha particle radiation, something along those lines. All right. So you start off with radium. Now, radium is, they tell you that the atomic mass or the mass number, it's right here, is 222. All right. So we write 222. But note that on the periodic table, and let's see if I can do this. If I bring up the periodic table up to here, hopefully you guys can see that. The periodic table shows that radium is down here, has an atomic number of 88. So I would put 88 on the bottom. All right. And let's do that, see if all this works. And then, so it says it's alpha particles so that I know that it produces an alpha particle. So just by this alone, I start off with radium 222. It produces an alpha particle. The question is, what else does it produce? And this is where the balancing comes in. Since I know that the mass number has to equal the same on both sides. Since the left of the arrow is 222, the right side has to be 222. So I go, well, 4 plus what equals 222? So I just take 222 and subtract 4, and I get 218. Cool. And then I do the same thing with the bottom. The bottom is 88 on the left, so on the right, it has to equal 88. So 2 plus what equals 88? And the answer is 86. So I go ahead and look on my handy-dandy periodic table, and I look for element number 86, and I see that that is radon. Okay, radon. So I put the Rn for radon, and I am done. This is the balanced nuclear equation. All right. This is the balanced nuclear equation for the alpha decay of radium 222. All right, and there you go. So that's alpha particle production, and that's how you balance. So now I'm going to show you an example for beta particle production. All right, so you have this. Hopefully you have written that down. And now I'm going to erase. All right, going to erase. And we have beta particle production. Now this is a decay for radioactive nuclides in which the mass number remains constant and the atomic number increases by 1. The net effect is to change a neutron into a proton. And it produces a beta particle, which is a high-energy electron emitted by a neutron in the nucleus as it changes into a proton. So the symbol is this. Since it is basically an electron, we say that its symbol is an E. Since it has no mass, remember electrons do not have mass, the mass number is 0, but the atomic number or the charge would be -1. So this is the symbol that we will use for a beta particle. Now, since nuclear stability depends upon the neutron-proton ratio, beta decay occurs to increase stability by changing that ratio. In this case, since it changes a neutron to a proton, if you have too many neutrons, in other words, the number is greater than 1.1, that ratio is greater than 1.1, this will reduce that ratio. All right? So it increases the atomic number by 1, but the mass number remains constant. Now, an example for this would be if, let's say we have carbon 14, and it says it undergoes beta, okay? And this symbol, like a B, is a beta decay, represents beta particle decay. So we say carbon 14, it tells you this, and it tells you that. Well, since it's carbon 14, I know that the symbol is C. The mass number right here goes on top is 14. And carbon, according to my periodic table, has a atomic number of 6. So I go ahead and I have that as my starting point. And since it's decaying a beta particle, I know that means for sure it's going to produce a beta particle. The question is, what else does it produce? So again, just like before, I have to balance out the mass numbers and the atomic numbers. So the mass is 14 on the left, so it has to equal 14 on the right. So 0 plus what equals 14? And the answer is 14. Now, this is a little bit trickier. I have to do the bottom as well since you're dealing with the negative number. -1 plus what equals 6? So that's basically 6 minus -1. That means 7. 7 plus -1 gives you 6. And according to my periodic table, element number 7 is right here. It's nitrogen. All right. And so I put the symbol N for nitrogen. And that would be the balanced equation for beta particle decay of, that would be for the beta particle decay of carbon 14. All right. So as an example, move that up, we have that. Okay. So that's beta particle. See, we're halfway done with this. Now, the last problem is, remember, this helped you out if you had too many neutrons. And if you notice, if we take that number and we divide 14 divided by 7, 14 divided by 6, that's going to give us 14 divided by 6. There are 8 divided by 6 because there's 8 neutrons. Remember, you subtract these two to find the number of neutrons. So 8 divided by 6, that'd give us a ratio of like 1.33 neutrons divided by protons. Whereas here, 14 divided by, 14 minus 7 is 7, so there's 7 neutrons. Divided by 7, that's 1.0. Well, remember, the ideal number is 1.1. 1.33 is further from 1.1. This, therefore, is more stable. And again, that's the whole purpose of doing any and all of these. Now, this occurs if you have too many neutrons. Well, what happens if you have not enough neutrons? You have too many protons. Well, in that case, two separate processes can occur, and they both can occur, they both end up with the same results. One of them is positron production. So a mode of nuclear decay in which a particle is formed that is the same mass as an electron but opposite charge. That the net effect is to change a proton to a neutron. All right. So what happens here with this is that a proton can become a neutron by emitting a positron. Now, I didn't go into this, but if you're wondering how a neutron could turn into a proton or whatever, the easiest way to understand it is this. You know that an atom is made up of smaller particles. You know that there are protons, which are positive. There are neutrons, which are neutral. And you have electrons, which are negative. Now, both protons and neutrons have a mass of 1. Okay? So they have a mass of 1, whereas electrons have a mass of 0. So the reason why these are 0 is because electrons are so much smaller than either protons or neutrons. The best way to think about it is electrons are these itty bitty tiny particles, and neutrons and protons themselves can be broken down into smaller particles. Now, these smaller particles are most often called quarks. Okay? Quarks. And if they are inside a proton or a neutron, they're called quarks. And there's many different varieties. But note that some quarks are positive and some quarks are negative. And they all have the same mass as an electron, basically 0. Now, it's not really 0. It's just so small in comparison to the proton or neutron that it's considered to be 0. So, if protons and neutrons are made up of these quarks, if a negative quark leaves, we call that a beta particle. All right, that's a beta particle. If a positive quark leaves, we call that a positron. Okay, which is a positively charged electron for all intents and purposes. All right, it's a positive electron. And if you have these are equal, let's say in a neutron, if you lose a beta particle, if these two are equal and you lose a negative, you become positive. That's how a neutron can become a positive proton. Likewise, in a proton, protons have one more positive quark than negatives. That's why they have a positive charge. Well, if they lose that positive quark, these two become equal, and you end up with a neutron. I know, it's really confusing. I'm sorry. But it is, in fact, nuclear chemistry, so it's supposed to be a little bit tricky. But anyways, positron production, as I said, its symbol is 0 on top, 1 on the bottom, and it's the same thing as an E, but it's a positive one. And with these, the atomic number decreases by 1 and the mass number remains constant. Let me show you an example. So let's say we have sodium, Na22, and it says it undergoes positron. Okay, So in the problem, it actually says positron. So we start off with sodium 22, sodium, Na, mass number 22. On my periodic table, I look and I see sodium. Sodium's right over here. Its atomic number is 11. So I go ahead and I put 11 there. And then I go ahead and say it loses a positron, emits a positron. So I put the positron here, positive 1, 0. And I go through the balancing process. 22 is equal to 0 plus, well, that's 22. 11 is equal to 1 plus 10. And again, I look on my periodic table and I see that 10 is over here and it is neon. All right, so that is neon. So I have Ne. All right, now something else. If you look here, it says positrons usually collide with a surrounding electron. So this positron is like the antiparticle for an electron. And when it collides with it, since the electrons are outside of the nucleus flying around, it will almost always collide with it. And when it collides, it leads to this reaction called the annihilation of matter. I just think that's pretty cool right here. All right. And, oops, get back here. And it basically emits a high degree of energy. This energy is called gamma radiation. So in addition to this, whenever you have positron emission, you also need to include a symbol for a gamma ray. Now, gamma ray is basically something like that. And it looks like a really kind of a weird Y type situation. If you just use a Y, that'll be fine. Technically, it's a Greek letter G for gamma. All right. Now, there's another process that does almost exactly the same thing. And this is called electron capture. Now, electron capture is a mode of nuclear decay where a proton absorbs an electron. All right. And since this is capturing it, if I say it undergoes electron capture, all right. So electron capture, let's say, is down here. Again, if we have sodium 22, and in this case, since it's capturing it, not emitting, that means the electron is actually a reactant. It's the only one in which the particle, instead of being on the product side, is on the reactant side. So I go ahead and I balance it. And I have 22 plus 0 equals 22. 11 plus negative 1 equals 10. And if you notice, it also produces neon, neon 22. And since, again, the electron going in will react with a positive quark, it also emits gamma radiation. Okay? So you have to make sure you include that little squiggly on the end. So another example would be mercury 201. It captures this inner orbital electron to produce gold 201. So the mass stays the same, but mercury loses an atomic number, basically, since it gains a negative 1, becomes 79, and 79 is gold. So it's the exact same process. All right. Now, here's, again, a diagram showing additional examples of each one. And just keep in mind that with gamma rays are produced with both positron production and electron capture. You got to remember to add that every time. All right. So gamma rays are produced with both electron capture and positron production. Now, the next thing I want to talk to you guys about, trying to go faster here. I mean, this is all the information you need in order to at least balance the equations. and the main thing they're going to be testing you on. But also, it's important to note that many large nuclei must undergo what is known as a decay series before they reach a stable state. Now, a decay series is a series of different nuclear reactions that happen in succession. For example, let's say you have uranium here, uranium-238. Now, it's a really big nucleus, so it undergoes alpha particle production. Boom, and it becomes thorium-234. All right, it lost 4 in the mass. Remember, alpha particle is the only thing that loses mass. But it also lost 2, and it goes down the periodic table by 2. But then, now it has far too many neutrons compared to protons. That's more of a problem. So it undergoes beta decay, and it keeps the same mass, but it goes up 1 in atomic number to become protactinium, and then it becomes uranium again from another one. So uranium, now the neutron ratio is better, but now it is far too large. So over time, it then does a couple more alpha particle productions, each time losing more. And it just keeps doing this over and over and over again until finally it ends up with a stable nucleus. Lead-206, for example, is a stable nucleus because it is below 210. All right, it's 209 mass or lower, and it has a decent ratio of of neutrons to protons. Okay. Next, something that people often worry about are the effects of radiation. Well, we're not going to go too much in detail on this, but just a few things to let you know. So radiation damage to organisms is classified as either somatic, right, which is damage to the organism itself. So if you are exposed to radiation, if you yourself get sick, then it's considered somatic. And this occurs primarily because radiation tends to wreak havoc with your DNA, all right? And in an individual cell, if your DNA gets messed up too much, you learn this in biology, it dies. And that's what causes this sickness. If you have too many cells that die, you're going to be sick or even even die. Too many of your cells die, then you die, all right? And it could be immediate if massive dose of radiation is received, or it could take years to manifest if a dose was small. Now, the most common form of somatic damage occurs, and we call it cancer. As you guys learned last year in biology, hopefully, if you get a mutation in your DNA that prevents it from stopping to replicate, then it can, we call that cancer. And the cell just keeps on reproducing over and over and over again and creates a tumor and robs nearby cells of nutrients and basically kills the overall organism that way. All right. So usually cancer. Now, another problem that can occur we call genetic. Now, genetic is damage to the genetic machinery of reproductive cells. Now, the key thing is this creates problems that often manifest in the offspring of the exposed organism. This is, I cannot tell you how many times people say, oh, if I get radiation exposure, I'm going to become a mutant. All right. Despite what you read in comic books or watch in movies, no, if you get exposed to a whole bunch of gamma rays, you're not going to become the Hulk. Instead, you probably just die or get cancer. All right. But what could also happen is that it can mess with your genetic machinery. In other words, with your reproductive system. And this could cause birth defects in your children or cause you to not be able to have children. Right? Too much radiation can actually sterilize you. So these are the two main types, somatic and genetic. In none of these, however, can you actually mutate. Once you get your DNA, boom, that's it. It's not going to change who you are. You're not going to suddenly grow a third eye or, a couple more arms or anything cool like that. Sorry. And there are certain factors that determine the biological effects of radiation. First is the amount of energy of the radiation. More energy means more damage. So some types of radiation, such as gamma rays, have a lot of energy. Therefore, they can do the most amount of damage. Alpha particles also, primarily gamma rays have the most amount of energy. Then is the penetrating ability of the radiation. Oops, get back there. Gamma radiation penetrates the deepest. It goes through the most amount of materials. But beta radiation only penetrates maybe about a centimeter into your skin. And alpha particles are actually blocked by the skin. So they may cause like skin damage, but they won't actually cause anything inside if you're being exposed from the outside. So those are actually safe to hang around. Next is the ionizing ability of the radiation. The more ionizing it is, the more harmful. Ionizing basically means its ability to remove electrons from cells. You remove electrons from cells, they become ions, and that can cause damage to you. Gamma radiation is not very ionizing, but alpha is. So see, there's all these different factors that you have to take into consideration. It's actually quite complex. And then finally, the chemical properties of the radiation source is also a factor. If your radiation source is inert, in other words, chemically does not react with you, it could just pass right through your body without causing much damage. However, if you have a reactive chemical like iodine, for example, radioactive iodine is very dangerous because it's like an alpha particle emitter, and it's beta particle, my mistake. It's beta particle emitter. But if you have, let's say, some salt that has this radioactive iodine in it, if you eat the salt, the iodine incorporates itself into your body and can slowly keep on hurting you over a long period of time, which can cause serious damage. All right. So all four of these factors are important when considering the effects of radiation. And as far as short-term exposure to radiation, a lot of people are concerned about, hey, if I get an X-ray, for example, or you go into the dentist and they put this big lead apron on you, and then the dental technician actually leaves the room before the X-ray. And you're going, is this safe? Well, it actually really is, because if you get a shot of an X-ray, that doesn't do a whole lot right away. It's over a long period of time that these problems occur, okay? And you can see like X-rays only give you about 50 millirems, all right? And you don't start having any problems until you start getting up into the REMs. So basically you can have, I don't know, I'm not doing the math right now. Let's say you can have like 100 X-rays in a year. Then it can actually start doing some damage to you. If you're only getting like 5 X-rays a year or something, it's no problem. The poor dental technician, though, they may give, 50 X-rays a day if it's a busy dentist office. And therefore, they have to worry about this as the exposure is cumulative. All right. And you can see that we have sources of radiation, small amounts all around us. We are even radioactive. So there's radiation all around us, nothing to worry about unless it's actually near a, nuclear power plants or any large source of radiation. All right, sorry for the long lecture, but there it is. Good luck, and hope this helps. Y'all take care. If you have questions, please come to tutorial.